I now, in this video, want to introduce you to the analysis of inclined plane problems. A block on a frictionless plane we'll start with. So we've already started that. In an earlier video, we extended our free body diagram, force diagram, thinking into this arena. And what we discovered there is that gravity, which acts straight down, can kind of be subdivided into a parallel part, parallel to the plane, and perpendicular to the plane. So we're going to look at three scenarios here, increasingly steep angles, theta, phi, and alpha. We'll put a block on there and we'll kind of see how the progression goes. So here we have gravity was always act straight down, but now we have part of that that's perpendicular, not the entire amount. This is the proportionately correct size. I'll call it the perpendicular force. And we have a parallel force. So those two together are equivalent to the weight mg. And now I can take this parallel force, and what I just did is moved it over here. So basically you see this weight is broken up into F perpendicular plus F parallel. I say plus because that's vector notation. We'll study that soon. Okay, these two are perpendicular to each other, so they are really, when two physical phenomena are perpendicular, they often are can be considered independent of each other. And just to note what I just said, mg, the weight, treated as a vector, this blue vector can be thought of as the addition of the parallel and perpendicular vectors. When you do vector addition, these two add perpendicularly like this to give us the weight. Okay, more on that later. Let's do the practical analysis here and see how it goes. What you notice is this is the same angle as this. These are similar triangles. Okay, so I could go into more detail on that. I'll just let it ride. I hope that makes intuitive sense. You can prove it if you want. I'll assume it's okay for the time being. And we also have the normal force. Normal is normal. And because there's no acceleration in this direction, perpendicular to the plane, then the normal force is equal to the perpendicular force, the part of gravity that's causing this block to be pressed into the inclined plane. Second one. Okay, gravity is the same as before, but now the perpendicular force is smaller, the parallel force is larger. The parallel force then is what tries to accelerate this down. We'll get to that. But the normal force being equal and opposite to the perpendicular force, you notice the normal force went down from the first one. We'll call this angle phi because it is. This angle is the same as this angle. And now we can bring the parallel force along, and we see that these two add together as vectors to give us this. And we can treat these independently because they're perpendicular. Finally, we have mg. And we have a relatively small perpendicular, a relatively large parallel force. There's the normal, which is same size as the perpendicular. And we have alpha. There's that angle. And there's the two components added together to give mg. All right. Trig analysis on this. Here we go. It's nice to know that we have a right triangle, because right triangles, here's a right triangle. They're easy to deal with. In fact, sine of this angle, if you take the sine of this angle, opposite over hypotenuse. Opposite is F parallel, hypotenuse is mg. We can now solve for the parallel part of the force. It's mg sine of theta. That's marvelous. That's something you want to kind of either commit to memory or be able to do this diagram and determine it just by looking at the geometry, or working out the trig, I should say. And then cosine of theta. Cosine of theta is adjacent over hypotenuse, so F perpendicular over hypotenuse, which is mg. So now we can get the F perpendicular, which is mg cosine of theta. This is really going to be useful. Let's see in particular here, get a start on its usefulness. The sum of the forces in the perpendicular direction is 0. All right, it cancels. no acceleration. So we can say that the normal equals the perpendicular force. And the perpendicular force is mg cosine of theta. Well, that's going to be very useful. The normal is mg cosine of theta, not mg. So now you know the particular way in which the normal force is altered by this angle that the block is on. If it's on a flat surface, theta is 0. So this whole thing is 1. So normal is mg. We already encountered that. The normal is equal to the weight. If theta is 90 degrees, this becomes 0. No normal force. So this is the particular and specific value of the normal force for any angle theta. That will be really useful because we're going to deal with friction in very short order. Okay, now it's time to put those ideas into practice with a couple of examples. So we'll actually compute the acceleration of a block going down a ramp. First of all, frictionless. So the mass is going to slide down from the influence of gravity without any opposition. That should be pretty easy. But it's not all mg trying to cause it to accelerate down the ramp. Okay, let me draw this out again in detail. We have F perpendicular, we have F parallel, we have our angle theta, same as the angle of the ramp, and there's F parallel again. So I constructed this similar triangle. And if I asked you, which particular force is it that's the impetus for the block to go down the ramp? And you'd say, what is impetus? And I would say, cause. And then you'd say, oh yeah, okay, well it's the F parallel. So it's the parallel part of this that's trying to make it go down the ramp, not the perpendicular. It's trying to press that into the ramp, right?
Basic concept.
Yes, A is F net over M, which is our basic idea, and the net force is the parallel force. Now, I could just cut to the chase, but I'll rederive what we just did a minute ago, or in the last video, or in the last slide, I should say. So sine of the angle theta equals F parallel over mg. Sine of this is opposite over hypotenuse. Now F parallel is mg sine of theta. So there it is. We already just had that before. So the acceleration then is F parallel over m, F parallel over m. M's go away, and we have our answer. We're all excited about that. A is g sine of theta. Now, if that made sense, great. Let's move on. If it didn't, back up a little bit and listen to it again. So now we're just going to add friction. All right, we have the same scenario, but we have sliding friction. It's going down the ramp, and I'm going to show the normal force in here as well. It's going to be a little bit instructive. So the net force now is not F parallel, but F parallel minus friction. So there's the equation. You just have to deal with friction, but we're equipped to do that now. F parallel mg sine of theta minus friction over m. Friction is mu k normal, our definition of friction, and we now have a definition of the normal, which is F perpendicular as well. Let's expand that out. So it's mu k mg cosine of theta, the perpendicular, or the normal, mg cosine of theta. So let's put it all together. There's the equation. Mg sine of theta minus mu k mg cosine of theta over m. M's go away, and we have A is equal to g sine of theta minus mu kg cosine of theta. Isn't that a beautiful result? And I hope you appreciate this little tidbit of physics that you just learned.